today we're going to talk about equilibrium. So in the last video we talked about stoichiometric and limiting reagent reactions where you had a reaction like A plus B yields C, and then either A or B is going to run out and then the reaction kind of just ends. Now equilibriums are kind of a bit different. You could start off with your reactants like these, and then you would slowly start to form products and you'd use it for your reactants. But then at some point, the concentrations are kind of just going to stabilize at this point and nothing's going to run out. So this is what we call equilibrium right here, their equilibrium concentration. So what equilibrium actually is it says that the forward rate of a reaction equals the reverse rate. So if we had a generic reaction like A plus B yields, and the equilibrium arrow is drawn like an arrow both ways, or if you want to be fancy, you can like draw this half arrow, yields C. What's happening is A and B is forming C, we know that, but now also C has a reverse reaction where it's forming A and B. So the rate at which this is being used up and it's getting formed, when those two rates are equal, when it's getting formed and consumed at the same rate, we reach equilibrium. So there's still reactions happening, but there's no net change in the concentration. We don't notice anything. Now the mathematical approach we have to equilibrium is through the mass action expression. Mass action expressions with capital K. Basically, for this you can use concentrations or pressures of gas. So you can use aqueous things or gases, but you can't use liquids or solids. So if you have a liquid or a solid in your reaction, you're just not going to include in here. And what the mass action expression is, you're going to multiply your two products, or however many products you have, and then put it over your reactants, multiply together. And then of course some of these have coefficients. So the coefficients are their exponents. So if it's 2a, that means it's going to be a squared here. And if it's 3c, that's just going to mean it's c cubed. So that's our mass action expression. Note that K is unitless. Even though you can get units for it, it is meaningless in any context. So whenever you have a K value, you just leave it without units. Now let's say I should mention before I go ahead that this can be aqueous or gases. So it can be like this with concentrations, but it can also be written if you had gases like with pressures. So if I write the same thing, I could say the pressure of C cubed times the pressure of D. This is the same mass action expression, but in terms of pressures, if these were all gases, times the pressure of A squared times the pressure of B. So this would be the same thing as this. Now, gas can be written with either one, but these two are a bit different. This expresses equilibrium in terms of pressure. So it's really K sub P. And then this expresses equilibrium in terms of concentrations. This is Kc. There's a nice relationship that this equation, I believe, is on your Chem AP formula sheet, where R here is equal to 0.08206. You're given that constant. And then T is in Kelvin. And then delta N is the change of the number of moles of gas. So here in our products, we have 2 moles of gas by this coefficient. And here we only have 1 mole of gas. So that means our change of moles of gas is going to be 2 minus 1 equals 1. So our change is an increase of 1. It could have also been a decrease in 1 if it was 2 here and 1 here. For example, then it would have been 1 minus 2 equals negative 1 and no problem. Just plug in negative 1 in the formula. So now let's talk about if we had more than one reaction, like here, and we wanted to find the overall K value. So A plus B equilibrium with C, and then C is in equilibrium with D. And I want the K of the reaction for A plus B equilibrium with D. So of course, you could see that like if you add these reactions, that the C's are going to cancel and will form the desired equation of A plus B equilibrium with D. But how do we find the K value for that? So if this first reaction has a K value of K1 and the second one has a value of K2, to get this K where we added the two reactions together, it's equal to K1 times K2. So adding reactions is the same as multiplying their Ks. Now, let's say we wanted to flip it. So let's say I wanted D plus A plus B yields 2C. So this looks a bit intimidating, but you'll notice that instead of adding these two, we're basically going to flip this expression. And then then it's going to be like D is in equilibrium with C. And then we add them. And now if we add them, we see it'll be A plus B plus D yields 2C, like this. So we had to flip it, and then we had to add the reaction. So to flip a reaction, to flip the second one, K2, instead of using K2 as its equilibrium, we're going to use 1 over K2. That allows us to flip a reaction. So 1 over K2 is going to be the equilibrium of this flipped reaction. And now we can just add them as we did last time by multiplying this 1 over K2 times K1. And our last thing we could do is adding coefficients. So let's say we wanted to double it. A plus B equilibrium with C, let's say that's K1. And then instead we wanted 2A plus 2B yields 2C. Then it's just going to be K1 squared. And then of course if you wanted to add that with something, you could multiply it by like K2. If we wanted to add to the reverse of a third reaction, we could just multiply by 1 over K3, and so on until you get whatever desired reaction you want. Moving on, let's see how to actually solve an equilibrium problem. So let's do this one, for example. Again, it can be with concentration, molarity, or it can be with pressures as ATM. So in this equation, or in this problem, we have pressure, ATM, and it says, consider the reaction to the right. System starts with 0.50 ATM of A. So this ice chart, all it does is I stands for initial. This is your initial concentration or pressure. C stands for change. And then E stands for your final equilibrium value. Other schools use other variations of this, but it's the same idea. So our initial of A is 0.50, and then our initial of B is also 0.50, and we have 0 of C. Now to see our change, these are in the reactants, and there's nothing here. So these reactants are going to form a bit of products. So the change is going to be minus something, so that it can form some products. Change of this is also going to be minus, because it's also a reactant, and the change of this will be a plus, because we have some product being formed. Now, minus what? We don't know, so we're going to title it as X. So this is also going to be minus X, and this is also plus X. However, whatever, plus 2, plus X. However, notice how this is 2A and this is B. So 2 A's are reacting for every B. That means the change here is going to be minus 2X, and this is only minus 1X. Because every 1B that reacts, 2 A's react. And then 2 C's form, so this would be plus 2X. So at equilibrium, this is going to be your initial, and then with your change. Same thing here, your initial with your change. And then here is going to be 2X, because it's your initial plus your change. So now we can write the mass action expression for this. So again, it's your products multiplied together, so our only product is C, and C is 2X, and then we're going to square it. Note when we square this, is going to be 4X squared, the 2 gets squared as well. Then we're going to put it over our reactants multiplied together, so we have 0.50 minus 2X, and that thing is squared, because we have a coefficient of 2, and then B is 0.50 minus X. Now all we're going to do is set this equal to your Kp value, because this is in terms of pressure. So it's asking here, if the system ends up with 0.20 ATM of C, what is the value of Kp? So 0.20 of C, that means 2X here, your final equilibrium, is going to be equal to 0.20. So 2X equals 0.20. That means X equals 0.10. That means we can plug in all the X's here to be 0.10. And then just put this in your calculator and you'll get your Kp value. So moving on, you could have also been given a Kp and then been asked to solve for what's the final concentration. So let's say in a different scenario, we end up with 2X squared over 0.50 minus 2X squared. That's a Kp. A nice math trick. Instead of like multiplying this on both sides and then foiling this out, if you have a squared at the top and bottom, you can just square root both sides. This is a very nice trick that can save you a lot of time. So always know if you see squares, you want to do that. Your last resort is to do a quadratic. Of course, you can solve it, but it's much easier to just square root. When we square root this, it's just going to be 2x over 0.15 minus 2x equals Kp. And then they would probably give you a Kp. Maybe it's like, I don't know, I'll just say 428 randomly. And then this is just a linear expression. You'll just multiply this on both sides. So multiply it. And then distribute this. And then solve for x. Basic algebra from here. Another thing we're going to talk about now is Le Chatelier's principle. So Le Chatelier, in short, all he says is if you add stress at equilibrium, it's going to shift the equilibrium. And we'll talk exactly what that means in a sec. It's a lot easier than you may imagine. So let's say we have A plus B. Let's see. You might tell I like that reaction. The first stress we can add to an equilibrium would be if you change concentration. So let's say this thing is at equilibrium right now. And then I added some more A. If I add more A, it's like I add more stress to the equilibrium here. So if I add more A, it's going to end up forming more C. That's all that means. And then because it's forming more C, we call this the equilibrium is shifting right. Because it's literally like shifting right and forming more products to the right, as this arrow shows. And vice versa, if we added more C, then it would shift left and form A and B. And then the equilibrium would shift left. That's the first stress. The second stress would be something like volume. Now, volume would only depend on gases. So let's say this was really 2B and this was 1C. And then this was like a solid. So notice how, let's say we increased the volume of our container. If we increase the volume of our container, that's going to favor the side with more moles of gas. So here there's 2 moles of gas and here there's 1 mole of gas. So it's going to favor this side and it's going to shift left. If we decrease the volume, it's going to favor the side with less moles of gas. So that's going to favor this right side. So with that being said, the third thing would be like, let's talk about neon. So anything in the noble gas column, like your last column in the periodic table, could be neon, argon, those are the most common ones. That's called an inert gas. So even though adding it would increase the total pressure in your like container, it's not going to affect the equilibrium because it's inert. It doesn't react with anything. Even though it increases the total pressure, the pressure of these still stay the same. So the equilibrium doesn't shift anywhere, it stays the same. And now the last thing you can add is heat. This one is a trickier one. Not really. So let's say this reaction was exothermic. Exothermic means it releases heat. Exo is like it releases. So the way I like to do these problems is the moment it says exo or endothermic, here it's exothermic, I'm going to say heat is on this side because it releases heat as one of my products. And now let's say the question is asking if we add heat, which way is it going to shift? So if we add heat, we can kind of just treat this like a reactant. So if this was just a reactant and we increased it, then you'd say, oh, all right, it shifts this way. It's the same thing. If you increase heat, it's going to shift that way. Pretty much behaves like a reactant. And the other way, if it was endothermic, that means heat is entering. That means heat would be on this side as a reactant. And if you increase the heat, it's going to shift to the right. And if you decrease the heat, it's going to shift to the left. So all Le Chatelier's principle says, if you add stress at a system in equilibrium, it's going to like shift the other way to mediate that stress. Next thing we're going to talk about is called the reaction quotient. So all the reaction quotients, a fancy way, it's the same exact calculation as K. So if the way you calculated K in one problem was like the concentration of A squared over B times C, then the way you'd calculate Q is going to be the concentration of A squared over B times C. It's the same thing. So then what does it even mean, you may ask? K is the equilibrium constant. Now Q says, where am I in the reaction right now? So even though the equilibrium constant might be like 400, then this reaction quotient might not be 400. Even though at equilibrium it may be 400, right now you might not be at equilibrium yet. So if you calculate Q and Q is bigger than K, before I talk this, actually, I believe I missed one part where you might already know this, but if K is bigger than 1, it's going to favor the products, and if K is less than 1, it's going to favor the reactants. So at equilibrium, if K is more than 1, it's going to have more products, and at equilibrium, if K is less than 1, it's going to have more reactants. So anyways, back to that. Back to this. We use Q to compare it to K. So let's say you calculate Q, and it's less than K. I like to just put it on a number line. So here's my number line. 1 is like anything past this favors the products, anything past this favors the equilibrium, or favors the reactants. We don't even need this one, to be honest. But let's say your K is here, and then I find my Q to be bigger. That means here's where my reaction is right now, and here's where it wants to be for equilibrium. So it's going to shift left. And then vice versa. If your Q is on this side, your reaction wants to be here, so it's going to shift that way. So that's all that says. If Q is greater than K, it's going to shift to the left, and if Q is less than K, it's going to shift right. One last thing that we'll talk about, and then we'll talk about Ksp, is this thing right here, the 5% rule. So what the 5% rule does, if you were to do this ice chart with your initial change in equilibrium, I would do, okay, minus x, minus 2x, plus 3x. And then we have a lot of annoying terms, like 0.10 minus x, then we have 0.10 minus 2x. And then this thing's still going to get squared. And then we have 3x. So there's a lot of x's here. What the 5% rule says is you can get a reasonably good approximation if you just get rid of these minus x's. So what we can do is we can try to just ignore this minus x and minus 2x and just say, all right, this is just 0.10. And then we solve for x. Now, what the 5% rule says, this is a good approximation, and it's okay to do this, if our solved value for x over the initial value right here, which would be 0.10, and then like times 100 to make it percent. If this whole thing is less than 5%, then you get a good approximation. Now, this like takes a second to do. And the way to like know if you should use the 5% rule, usually if your K is in like 10 to the negative 4 territory, maybe 10 to the negative 3, but anything like this or less, so like 10 to the negative 8, you're definitely safe. And that's because this K value is so small that x, the amount reacted, is going to be so insignificant compared to the starting. So we can kind of treat it that like nothing even happened, that this is just still 0.10 equilibrium. Because even though it will be minus x could be like minus 0.000004. So that doesn't really matter. So if our approximation is within 5%, we're good. So on your AP sheet, on your AP Chem test, if your K value is like 10 to the negative 4, you should probably get saying, no, let's use the 5% rule, make things easier for ourselves. And then on your paper at the end, I would actually show the 5% rule and then say less than 5%, good approximation. Now let's talk about the last thing here is Ksp. And what Ksp, it's a new concept. It says, okay, AgCl is a solid. It's insoluble. However, that was kind of a lie that your teacher told you. This is a tiny bit soluble, and a tiny bit amount forms Ag plus aqueous and Cl minus aqueous. And this is a tiny equilibrium. Of course, there is way more solid than this. So like we said, if K is less than 1, it's going to favor the reactants. So K here, it's not only less than 1, it's super small because it really favors this side. Because it's a solid almost 99% of the time. So K's, you could see stuff like crazy, like 4 times 10 to like the negative 11, stuff like that. So with these problems, when you write the equilibrium expression, note how this is a solid. So it's not going to be in our equilibrium expression. So it's just going to be our products multiplied together. And then that's it. You don't have any reactants. So our K value is just going to be this. Now for solids, it's specifically called the Ksp. It's like I believe soluble product or solid product, something like that. But anyways, with a solid that's dissociating, it's called Ksp. And it's very simple, just like that. And all this calculation is going to do is you're going to go the same way, except your initial value, you don't really care about it. You may be given, like this is just like 0. And then plus x, and then this would be x, and then you're just going to set up x squared equals your Ksp value and solve for x, how much Ag plus you have. It's a relatively simple calculation. Now, one important thing I should talk about is molar solubility. What molar solubility is how much is soluble per mole. So it sounds like a weird concept, but how much of this thing is soluble per mole? That's the molar solubility. Now, the easiest way to get this is in your ice chart here, even though this is a solid and we kind of ignore it, you can kind of cheat and say the change here is like technically minus x. Because if you got plus x and plus x of this forming, technically you got minus x of this getting used up. So per mole, this is how much is going to dissociate, minus x. So if you want to solve for the molar solubility, it's just going to be your minus x in this right here. Now, this minus x, it has to be this specific one. It can't just be from here. And that's because, for example, if you had PbCl2 and you did the equilibrium, it's going to form Pb2 plus, let me erase this, plus 2Cl minus. So now you're going to have your ice chart with your initial change in equilibrium, and this is going to be 0, 0. And now this will be plus x, but this will be plus 2x. So you got to be careful about which one you're picking. This will still be minus x. So you would solve for x here for your molar solubility. So if you solve for x, it's your molar solubility, long story short. So for one quick problem, and then we'll end. Given that its molar solubility is this, what is the Ksp of Bi sub 2 S3? So we just first start off by writing the equilibrium reaction. So we got Bi2 S3 is in equilibrium with 2 Bi 3 plus 3 S2 minus. And then this is your solid, this is your aqueous, and this is your aqueous. So we're going to set up our ice chart. We always set up an ice chart for equilibrium. And then initially this, we don't really care, it's a solid, but we're going to cheat and say that this is technically minus x. And then we have 0, 0, plus 2x because there's a coefficient of 2 here. And then plus 3x because there's a coefficient of 3 here. This is going to be 2x because 0 plus 2x, 0 plus 3x is 3x. So we have, with our Ksp, note that our Ksp here is going to be Bi3 plus. This is going to be squared because it's got coefficient of 2. And then times S2 minus cubed because it's got coefficient of 3. So that's our Ksp. So we found Bi3 plus to be 2x. So we're going to do 2x, all of it squared, times our S2 minus is 3x. So 3x all cubed. And then that equals 4x squared times, what is that, like 27x cubed. And then that equals like x to the 5 times like 80, 108. So we have 108 equals Ksp. Now remember, it gave us the molar solubility. And we know that the molar solubility is minus x. So the molar solubility is equal to x. So we can just plug in this molar solubility they give us into here, then multiply by 108, and we'll get our Ksp. So, and one final thing to talk about, the common ion effect. We'll probably talk more about this, or not common ion effect. I should just say that if you started off with some of this, or some of this, if you start off with something, then you're going to form less of the other thing. And what I mean is, instead of, like here we started off 0, maybe we like produced 0.01 of each. If instead we had a little bit of S2 minus to start, then we would form a lot less Bi3 plus. And we'll talk about that a bit in the next video. So thank you for watching. Good luck on equilibrium.